Welcome back to the next video, everybody. This will be the third and final video on the first group, cohomology group H1. It'll be a quick one today. Let's start out by looking at the case that G is an infinite cyclic group or the profinite completion of an infinite cyclic group. Let's suppose X is finite, so G is acting on a finite set or a finite abelian group X. Let's let little g be a topological generator of big G, and let's let little x be in big X. We can certainly find integers k and n in the natural numbers such that g to the n x is x. I mean, if you act on x enough times by g, you're going to end up back where you started since x is finite, and such that k times x is 0. Again, that's just because x is finite. Okay, let's define a one cocycle f by f of g to the I equals 1 plus g plus blah, 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 plus g to the I minus 1 all times x when I is positive. Now, this is an easy little exercise for you, or maybe it's just obvious to you. I don't know. If I is bigger than j and I equals j mod kn, you can check easily that g to the j plus blah, blah, blah plus g to the I minus 1 is a multiple of 1 plus g to the n plus blah, blah, blah plus g to the n times k minus 1. Okay. And then it's also extremely easy to see that this basically by construction, this latter expression here just kills x. Okay. So when you do this times x, you get 0. Okay, and so what this tells us then is that f of g to the I depends only on I mod kn. And so you can extend f to a continuous cocycle on all of g, right? So if g is just infinite cyclic, you can just extend this definition to the negative integers, for example. And then if it's a profinite completion, you can just use density to extend the definition to all of g. Okay, and so if you go back to the previous video and you use an argument like the one we gave there, you can check that every cocycle must be of this form, actually. And so there's like 1 per x. And so we have the following result. Let's let G be an infinite cyclic group or the profinite completion of an infinite cyclic group. And let's suppose x is a finite G module. Then H1 of Gx is isomorphic to x mod G minus 1x. Okay? X because there's one of these cocycles per x, and then mod G minus 1x because of the definition of a coboundary. Okay, let's talk about a super important result right now that gets used somewhat often when applying this theory to other things like number theory. Let's look at Hilbert's theorem 90. If you take L over K to be a Galois extension, it turns out that H1 of the Galois group of L over K, comma L cross or L star if you like, is just 0. So H1 of G L over K L cross is just 0. It's just a trivial group. For a proof of this, you can check like Sayre local fields, chapter 10. This is proven in a variety of places, though. I think maybe even Silverman proves it in an appendix or something. Okay, let's look at an example of this in action. Let's let little n be a natural number, co-prime to the characteristic of our field K. And let's consider the exact sequence of GK modules, 1 to mu n, the nth roots of unity, to k bar cross to 1, where this map here is just the nth power map, which of course has kernel mu sub n. So this is going to be an exact sequence pretty easily verifiably. Okay, now the resulting long exact sequence of cohomology that we talked about 1 or 2 videos ago includes the following chunk: H0 of GK k bar cross, that's H0 here, to H0 of GK k bar cross, that's here, to H1 of GK mu sub n, that's here, to H1 of G sub K k bar cross, that's here again. Okay, now this first map is just the nth power map as we just discussed. And we know this last group is 0 by Hilbert's theorem 90. And so essentially by the definition of exact sequence, what you find is that this guy here, H1 of G sub K mu sub n, is isomorphic to H0 G sub K k bar cross, which is just K cross, right? The stuff in k bar cross fixed by everything in G sub K is definitely just K cross. Okay. Mod what? Well, mod the image of this map, which is nth powers of stuff here, which is nth powers of K cross by the argument I just gave for why this is K cross. Okay, and so this is kind of an important result. H1 of G sub K mu sub n is isomorphic to K cross mod nth powers. All right. So next time we'll go and we'll take a look at inflation, restriction, and briefly we'll take a look at cut products. So I'll see you then, and thanks for watching.